Hello. As we've seen already, there are two broad ways of representing change. One way is to assume that change is continuous, in which case we would use a differential equation. In other instances, we might assume that the change occurs at discrete time intervals, in which case we would use a difference equation. Here we're going to be looking at how to solve differential equations. We have statements for the continuous rate of change of a variable, such as the population size, and we want to work out how does the population size change over time for a given set of start conditions. Well, there are two broad ways to do this. The finest way is to find an analytical solution to the integral of that differential equation. However, sometimes that's very difficult, and in those cases we might consider the numerical integration of a differential equation. Now, the downside of numerical integration is that we don't fully understand its properties. We can only explore its properties rather like a simulation. But the upside of solving a differential equation numerically is that we can apply these solutions to virtually any differential equation we like. Well, how would we solve a differential equation using numerical integration in R? There's a variety of ways to do this, but the most commonly used form for integrating a differential equation that I know about is using the package dsolve. And within that package dsolve, there's a really nice function called ODE, that's ordinary differential equation. Unfortunately, ODE has a particular structure that takes a little bit of time and thought to understand. Here's how ODE is structured. We have y times function, parameters, and method. And I'm going to go over and try and explain each of these different arguments to that ODE function. Y gives the state variables. These are the dynamical variables that we're seeking to integrate. Sometimes it may be simply a matter of population size of one particular species that we're interested in, or it could be several species, or of course it could be some other rates of change. So we can solve our particular problem not just for one state variable, but for a range, and we'll have a look at applications later. Now, when we're numerically integrating a set of differential equations, we need to define how long we want to continue the integration for, or over what range, and that's typically given in terms of time if our dynamics is occurring in time. But we also need to specify at what time intervals you want the output to be given. Of course, it's a integration, so what we are doing is working very small periods of time, but in order to report our output, sometimes we might want chunkier time intervals to do that. The function gives us the set of derivatives that we simply want to numerically integrate, and we'll have a look at the way that function is defined shortly. Now, when you've got a set of derivatives, then typically there's parameters, things like your intrinsic rate of increase or your carrying capacity. These are typically considered constant, and they're often termed in terms of p, and they're the parameters that are part of that function. Now, and here we're not going to be too concerned with the method, but this is just to note that should we choose, we could call up our own numerical integration algorithm. There is a standard, it's called ISODA, but also we could call up, should we wish, a Runge-Kutta method, etc. So let's see this in action, because it's probably better to view the ODE in action so we actually see what it's about. You'll get a clearer idea once we start to play with different models. The first thing I'm going to do is to call up the library dsolve, because this gives us access to that function ODE. Now here is our function that we are going to define. We're calling it C growth for continuous growth, and that function has to be defined in a certain way. We have got the parameter over which we are integrating, this is the times. We've got the list of state variables, this is the y, and we've got the parameters which we're calling parms. And everything within that function is defined here with the squiggly brackets. Now you'll notice that we have dn dt in terms of dn dot dt, but we could have equally called it my solution or whatever. There's nothing special about that dn dt. However, it does correspond to the rate of change of the state variable, which is y. And we're saying the rate of change of the state variable is equal to p square brackets 1, so that's the first parameter, times y square brackets 1, so that's the first and only state variable. So in many ways this is rather like dn dt equals rn, where simply r is an intrinsic rate of increase and n is a instantaneous population size. And what we do here is that we return a list with this function the way it's been defined, and that is the list of values of dn dt. Of course, what we have to do is to do a little bit more work. We have to get the ODE to use that function, which is why that function has been defined in very particular ways. Now let's have a look at the parameters and the way we define them. Here we've got p is equal to 0.5, so effectively our rate of increase is 0.5. We have y0, which is the start condition, I'm giving 2, and the time over which we want to report the integration is between 0 and 20 in steps of 1. Here's where we call up the solution now. Of course, I could call it anything I like, but here is the output. What do we have? Well, it's the ODE where we give the starting conditions, y is equal to y0. So to begin with, our state variable, and there's only one of them, is given the value 2. The times that we're integrating over is between 0 and 20. In our case, we want to report only unit time intervals. The function that we're passing to ODE is this continuous growth function, and the parameters are simply that value p. Now it will take some getting used to, but that's all ODE needs in order to work out the numerical integration of that individual function and report in discrete time intervals between 0 and 20. So here's how we plot it out. Between 0 and 20 give us the sol square bracket comma 2, and that refers to the second column of the solution. The first column of the solution, i.e. sol square bracket comma 1, is actually the time, but here we've used t rather than sol square bracket comma 1. And here is what the overall growth looks like. With r greater than 0, then what we have is a geometrically increasing population. Now it turns out that we could have solved this particular problem, this differential equation, analytically. We could easily find the integral for that and see that it's an exponential function. But this is just to show you how we can use these numerical methods to identify solutions and print them out. Now, here is a more sophisticated continuous time model for the rate of change of a population size over time, where here we have the component Rn, that's the geometric increase, and yet it's multiplied here by 1 upon n divided by k. K is often referred to as a carrying capacity. Effectively, K has the effect of putting the brake on N. As N gets really large, the overall rate of change of this population gets smaller and smaller because this fraction gets closer and closer to 0. In fact, as N approaches K, then this really does become close to 0. Now, this particular equation is very well known. It was first described by Pierre Verhulst, who called it logistique after the art of calculation, but really popularized by population biologists such as Raymond Pearl, who came to see it almost as a universal law of population growth. Now, it turns out that we can find a simple analytical solution to this differential equation. But here what I would like to do is to simply look through and see if we can find a solution using the dsolve, the ODE of dsolve. So here's how we find a numerical solution to the logistic equation. First of all, we have to define our function of the continuous time logistic, and here it is. There's the function defined strictly in terms of times, y and palms, as the ODE solver requires. We've got dn dt here, and notice now that we have two parameters, one standing for r and the other one standing for k, and yet we still only have one state variable, that's the n here that we see. And then we get a list which is returned from solving this differential equation. I should say that later on in the applications part, you'll see ways in which we can refer to these parameters by name, like r and k, and also you'll see an example where we've got more than one state variable. Now, let's have a look at how we define our parameters. Here's p at 0.5 for r, and here is the second parameter. This is k, and we're going to give it 1,000. Our start value might be 2, and we would like to simulate between 0 and 30. Here the integration is occurring over continuous time, and yet it's reporting only each individual discrete time unit. And here is our solution. Here's the ODE that we're calling it sol2. Y is equal to the start condition 2. The times for integration are between 0 and 30. The function that you're passing is the continuous time logistic, and the palms are given here. Now we can plot time against the second column of sol2, which is the population sizes integrated up to that time period, and I'm using type L to give a nice continuous line, and this is what we get. We get the familiar sigmoidal population growth that is very typical of the logistic equation, where we begin with effectively exponential growth until that 1 minus n upon k term starts to dig into the overall population growth, and the overall population size eventually reaches this asymptote, this upper level, which in this case is the carrying capacity of that population. Thank you for listening to this R-Labs tutorial video. If you found this useful, you might be interested in our free online Moodle course, or check out and subscribe to our YouTube channel.